Now we want to look at the derivative as a function. Instead of finding the derivative at specific points, we want a function that will define the derivative at any given point. Now remember, the way we found the derivative at a point was we were looking at the secant line and taking the limit as h approaches 0, or as the points got closer and closer together, the secant line would approach our tangent line. So we have two different forms of the derivative as a function. Notice the derivative as a function we've written there as f prime of x. So the derivative of a function with respect to a variable x is the function f prime, whose value is the limit as h approaches 0 of f of x plus h minus f of x divided by h. Then there's an alternative form for the derivative. F prime of x is the limit as z approaches x of f of z minus f of x divided by z minus x. Now I'm going to show you an example of finding the derivative using these formulas, each one of these formulas. First I'll use the definition derivative formula. And we have f of x is x divided by x minus 1. So if we use the formula, or the definition, f prime of x is the limit as h approaches 0 of f of x plus h minus f of x divided by h. Now in the past recordings we used x sub 0, and x sub 0 was a specific point, but we're going to use x here. So this is going to be the limit as h approaches 0 of f of x plus h. Well, that means we're going to take our function and we're going to plug x plus h in for x. So we'll have x plus h divided by x plus h minus 1 as our f of x plus h, minus f of x, which is what we started with, x divided by x minus 1. And this is all over h. Now you'll notice that we have a complex fraction, which means that I have two fractions in the numerator of my fraction. In order to eliminate the complex fractions, what we want to do is we want to multiply through by the common denominator by the fractions from the numerator. The common denominator will just be the product of these two. Now I can multiply by the product of these two as long as I multiply every term top and bottom by that product. So that will be x plus h minus 1 times x minus 1 times x plus h divided by x plus h plus minus 1 minus, and then x plus h minus 1 times x minus 1 times x divided by x minus 1. And if I do that to the numerator, I also have to do that to the denominator. So that's x plus h minus 1 times x minus 1 times h. Now this looks very complicated, but as we go through and multiply, we'll be able to simplify. Our x plus h minus 1s will cancel, and that will give us x minus 1 times x plus h minus our x minus 1s will cancel, and that will give us x. I'll put the x in front, x times x plus h minus 1. And in the denominator, we'll just leave that factored, x plus h minus 1 times x minus 1 times h. Now that is the limit as h approaches 0. On top, we'll need to FOIL and use the distributive property. X times x is x squared, x times h is xh, negative 1 times x is negative x, negative 1 times h is negative h, and then distribute. Negative x times x is x squared, negative x times h is negative xh, and negative x times 1 is positive x. And again, we're just going to leave the denominator factored, x plus h minus 1 times x minus 1 times h. This is the limit as h approaches 0. Now if you'll look on top, your x squareds will cancel, your xh's will cancel, and your x's will cancel, because we're left with a lot of opposites there. And that will leave us just with negative h on top. And on bottom we have x plus h minus 1 times x minus 1 times h. Now we're still not to a point where we can plug h in. If we plug h in, we'll still have our denominator being 0. However, since there's an h on top and bottom, I can cancel those. And that will leave me with the limit as h approaches 0, and I will have -1 on top, and on bottom I will have x plus h minus 1 times x minus 1. Now I'm at a point where I can plug 0 in. If I plug 0 in, my denominator will not be undefined. So if I plug in 0, I'll have -1 on top in the numerator. On bottom I'll have x plus 0 minus 1 times x minus 1, which gives me -1 divided by x minus 1 times x minus 1. And I can leave it that way, or remember we can also write that as -1 divided by x minus 1 squared. So that derivative of f of x, which is x divided by x minus 1, is -1 divided by x minus 1 squared. And that is using the definition of a derivative. Now let's find the derivative of f of x equals the square root of x. And this time let's use the alternative form. The alternative form is the limit as z approaches x of f of z minus f of x divided by z minus x. That's going to be, in this case, the limit as z approaches x of f of z means we plug in z for x, so that's the square root of z, minus f of x, which we were given, it's the square root of x, divided by z minus x. Now, if I just plug in my z, of course I'll have 0 in the denominator, or plug in my x, I'm sorry, if I plug in my x minus x will be 0 in the denominator. In order to make this a form that we can work with, we're going to rationalize the numerator. Now remember, to rationalize the numerator, I choose the conjugate. If I have the square root of z minus the square root of x, its conjugate will be the square root of z plus the square root of x. So I'm going to take this limit of the square root of z minus the square root of x over z minus x, and I'm going to multiply top and bottom of this fraction by the conjugate, square root of z plus the square root of x divided by the square root of z plus the square root of x. Now the reason I can do that is since the top and bottom of this fraction is the same, this is actually a unit fraction, so this is equal to 1. So I'm actually not changing my fraction's value, I'm just changing its appearance. So that gives me the limit as z approaches x. On top, I'll need to full square root of z times square root of z is z. Square root of z times positive square root of x is positive square root of zx. Negative square root of x times positive square root of z is negative, and I'll write it as zx also. And the negative square root of x times positive square root of x is negative x. Now on the bottom, I'm going to leave this factored as z minus x times the square root of z plus the square root of x. Notice I do that a lot. I leave the denominator factored because a lot of times once we simplify the numerator, we'll be able to cancel something, which we'll see here. The limit as z approaches x. On top you have the two middle terms are the same. That's why we choose the conjugate, because the two middle terms will cancel and we'll be left with z minus x. And on bottom I have z minus x times the square root of z plus the square root of x. Now these are the same, so I can cancel. That will leave me with the limit as z approaches x of 1 divided by the square root of z plus the square root of x. Now I'm at a point where I can plug in x for z. We're looking at the limit as z approaches x. So I can plug in there an x for z without making my denominator 0. When I do that,